I'm here with problem 16 on page 160 of Hungerford's Abstract Algebra Introduction. Notice this problem says, let I not equal to R be an ideal in a commutative ring R with identity. Prove that R mod I is an integral domain if and only if, whenever AB is in I, either A is in I or B is in I. So that's the challenge. The secondary challenge is that Brooke and Aaron think this video should be exciting. So I don't exactly know how to make a video on ideals exciting, but we'll see how that works. Time to begin. Here you go, Brooke. That's turning the page or something like that. Okay, so we're going to assume that I is not equal to R, and that's an ideal inside my ring. Now, what do I need to do? I have an if and only if statement in the theorem. So let's first just think about what kind of a thing is R mod I. If I have an ideal inside there, we know R mod I is the set of cosets, right? So this is a set of subsets of I. It's the set of cosets that look like A plus I, such that A is an element of R. Okay, so it's the set of cosets, and if I is an ideal, then this is itself a ring. Okay, we know that if R is commutative, that R mod I is commutative, and if R has unity, R mod I has unity by theorem 6.9. Now, what does it mean? We're going to say that R mod I is an integral domain if and only if some property holds. So let's think about that. Two directions. Okay, so assume R mod I is an integral domain. Let's see. So what does it take to make a ring an integral domain? Well, an integral domain is a commutative ring with unity not equal to 1. Okay, so that means that 1 is not equal to 0. Did I say that correctly? The unity element is not equal to 0. It's commutative, and it has no zero divisors. So A times B equals 0 implies A equals 0 or B equals 0. There are no zero divisors. Now, what's that look like for elements in R mod I? Okay, so this is the general meaning, right? Well, so let's visit that property to start with. First off, what does it mean that I is not equal to R? Well, if I is not equal to R, then notice that we know that I doesn't contain the unity element. Okay? So think about that. If and this is independent of this assumption, right? I not equal to R implies that 1 is not an element of I, since otherwise A equals A times 1 is in I for all A in R, right? Well, what's it mean to be an ideal? It means anything in the ring times anything in the ideal is in the ideal. Well, that would mean everything in R was in I, and that would contradict this statement. So what does it mean 1's not in R? Well, 1 not being in I means that 0 plus I is not equal to 1 plus I. So, in other words, you got that property whether or not this is an integral domain, right? Or whether or not that last property holds. So what do we really have here? I've got R mod I is a commutative ring with unity not equal to 0. Okay, if I'm assuming R mod I is an integral domain, that means this property holds, but it holds for elements of R mod I. So this is sort of my thought to the side. Thus, for all elements in here, what do elements in here look like? A plus I, B plus I in R mod I. Okay, for all elements in there, A plus I times B plus I equals 0 plus I. Okay, that's the additive identity. Implies, well, remember this is the implication, and I'm just putting in what elements of our actual ring looks like. A plus I equals 0 plus I, or B plus I equals 0 plus I. Okay, so that's what we have there. Okay, and so if I'm assuming this, I get that for free. Now let's think about what I'm actually supposed to try to prove. I'm supposed to prove that A, B in I says something. Well, let's think about what this is. The definition of multiplication means that this thing is equal to AB plus I equals 0 plus I, which means I. Okay. Well, how does that work? How can something be equal to I equals sort of ditto over here? Okay, so what does it mean that A plus AB plus I equals I? Well, that means that AB is actually an element of I. Well, how do I know that? The additive identity 0 is in I, therefore AB in I, right? AB is an element of I, implies, okay, so the only way that this can be equal is if AB is in I. That implies this is true. Well, what's that say? By the same logic, this means A is in I, or B is in I. Ah, well, that is exactly the condition that we were supposed to show. So we're halfway done. There you go, Aaron. Time to turn the page to the other direction of this thrilling and earth-shattering proof. Really looking forward to this being the top viewed video on YouTube. It's pretty breathtaking, a little bit risque. Maybe they'll give this one, you know, a PG-13 rating or something like that. But that's okay, all for the sake of math. Okay, so now what are we going to do? Well, we're going to now assume for all A and B in R, AB in I implies A is in I or B is in I. And you could basically make these if and only if statements. So since this is true, that means what? That means that for all AB in R, AB plus I equals I implies A plus I equals I, or B plus I equals I, right? Because that's what it means for B plus I to equal I. Okay, so what's that mean? Well, you can say if I've got any element in R, then certainly that means I can say something for all A plus I and B plus I in R mod I. The same thing is true. Well, what is that condition actually? This is the same as A plus I times b plus I equals, and of course I is the same as 0 plus I. So these are the same conditions, and a plus I equaling I means a plus I equals the identity, 0 plus I, or b plus I equals the identity. Okay, so that, of course, is the only thing remaining for R mod I being an integral domain. And there you have it, the thrilling, earth-shattering, and really exciting proof about ideals and integral domains.